to the committee for the invitation. It's a real pleasure to enjoy a balmy English weather after having been in the North Pole for a month, and I really enjoy this conference. So what I'm going to talk about here is, particle filter and application to inverse problems. This is inverse problems with a cause. So this was inspired by an inverse problem which really didn't want to be solved with many other methods. So it will appear in the beginning, and then it will appear again in the end. So this is work which was done with Erkki Sommersalo and our student Andrea Arnold, who's going to be finishing in May. So in order to frame this properly, we have this dynamic model here. So we have the forward model, doesn't say much here. And so the x dt is a function of t, x, and possibly theta here. We have some initial condition. And in the parlance of particle methods, and so in a different crowd, x would be our state vector. And in our case, the parameter vector theta is either poorly unknown, or, as it was the case for the, let's say, the problem which inspired all of this, it was totally unknown. People didn't have a clue about what this was. And in fact, a lot of the question, as it was posed initially, was what can we infer from the parameters? And there is going to be a follow-up. Are these parameters going to give us a clue about the type of patient that we're looking at? So, so f is our function, and possibly we have also the initial vector, which is the initial state, which is unknown. Then what we have is, as usual, we have a set of observations. So we have discrete observations here, and they might depend on the parameter. They will depend on the state, and as usual, there is going to be noise. And for now, we're assuming that the noise is additive, and you can think about your favorite noise. We don't have a problem. We have been whitening left and right, and Erkki will talk about this, and transforming if need be. And so the problem, the inverse problems, simply stated, is we want to estimate, if we want to follow the evolution of the vector, we want to estimate the state vector, and certainly we want to estimate the parameter vector. So depending on where you shine the light, you might go for a state estimation, or you might go for a parameter estimation. So what I'm going to present is going to address both of them, because in order to get one, we need to address the other one too. And this is all based on the observations that we have. So this is the villain, this is the culprit. This is a pet problem. And so we have our colleagues and collaborators in Denmark, and they have happy drinkers in Denmark, and a small cohort of healthy control people. So they are studying the brain functioning under alcohol. So what they want to do is they want to figure out what is going wrong. I mean, this study is this study is for cirrhotic liver patients and hepatic encephalopathy patients, but I mean, one can also think that this can be extended to other, say, brain problems, including aging brain, because they're looking at whether are the neurons or the astrocytes which are compromised under these conditions. So they had they were administering this marked acetate, which is only metabolized by astrocytes, and they are they're following the patients, and they want to know how efficiently the three different cohorts metabolize this. And so then they had measurements, and they had noisy measurements, and the measurements were essentially measurement of this mix of M1 and M2. And I'm not going to enter into the details because there is a lot of, let's say, units to explain here. So becquerel. So now let's set up a little bit of the stage here for a particle method. This is rather traditional in, let's say, in certain crowds. So what we have is we can think.
Sorry, the case is the previous thing are known?
Nothing is known.
Oh, nothing is known.
The case, this one we want to know, especially they would like to know the K2 and the K5.
Sorry, that's what you were looking for.
All, yeah. So we don't know anything, but we know the form. So we know that it evolves in this model here, it evolves in this fashion here, but we don't have the parameters known. And so we don't even have an approximate value for these parameters to begin with. There is yet another parameter, another scaling, which is a V0, which I'll show in the end, which was not known either. So, okay, so we have, let's say, as usual, in this context here, we would think about an evolution model where we have the state at the next time step, let's say +1, be a function of xj and theta, and then there is an innovation process here. And normally, but that's not going to be the case for us because we have more uncertainty here. We have that f is a known propagation model, and the propagation model is known in the form, but not in all of the details. Then people typically have an innovation process where they think that the statistics is known and it's independent of the state, and theta is a parameter. And then there is an observation model where we have an observation noise which is independent of the state. So we have already dealt at dinner last night about a linear Gaussian model for which we have the Kalman crowd here. Now we're going to go on and we're going to look at this problem where the problem is non-linear and non-Gaussian. And we have our data, dj here, which are our observations. And what we want is we want to really get a posterior for our state, x, and we're updating this in time. So these are sequential methods. So we have, oops, sorry. Okay. So first we evolve our state, okay, given the data that we had, the dj, and then the data comes and we're making sure. So the data is going to keep us on track. You can think of this as some sort of predictor, corrector, in a way. So you predict according to your evolution model, then the data comes, and then you correct if need be. So, so this is, Bayesian filtering here. So what we I have to keep track of the clock. There's one in front of me. All right. So I'm going to write, the standard formulas here. So we're going to write that the posterior of xj given dj, and we are expressing it in this form here where we are marginalizing, we're integrating in dj. So this is a step here. Then we get into the analysis step, and that's where Bayes' formula start showing up here. So we are writing xj conditional on dj plus 1 and xj plus, so we are writing now, we are introducing dj here so that we can invoke referent Bayes and make a switch here. So the reason for this is that this is the object of our interest, and now we're going to express it in terms of the portion here. There's a likelihood of, this depends on our data, which comes at dj plus 1, times this expression here, which depends on our, let's say, evolved state, which depended on the data that we had at dj. Substitution. So this is, again, we keep our eyes, we keep our gaze here on the objective, which is to compute this one. And we are using this formula. So I'm writing this, I'm reporting this as is. And then when it comes to this term here, I go up here and I replace it with the integral. And so now, this was in the continuous case. Now we're kind of like starting to see how we approximate the different pieces. So we assume that we have a distribution, the current distribution. So the j subscript indicates the current state, and the j plus 1 is the next one when we're advancing here. So we have it represented in this form here. So we have the samples and some, you can think of weights here. And now we are taking the formula, which is going to give us the probability of xj conditional on dj plus 1. And what we do is we replace this integral here by this summation. So we're approximating this integral. Now, in traditional, let's say, traditionally, and there is a lot of literature on this, a lot of jargon and a lot of opinions on how to do it. So what we would do, the way we would proceed here is we would go ahead and we would take a particle, a candidate particle from a distribution. We would compute a relative likelihood of the type. Let's take our candidate here, and now let's throw it to the wolves and see, how well it works. So we're computing how fit or how good the particle is in explaining the data which has come here. And then we are assigning, so we are giving a weight here to this particle. So we're rating this particle according to how well it does. And then we're resampling here, and that's the important resampling. And those which do well, they have a high probability of being chosen, and those who do well, they go out the door. So that seems like a very good idea, except that if anybody who has tried this has run into the problem of particle thinning. It gets very sparse. It gets very lonely for the good particles after a while, because in particular for problems or ill-posed problems, it's not uncommon that the propagation model, which is our prior essentially, what we're doing here is we're expressing what we know by stating how these particles propagate, and the likelihood they may be rather, let's say, orthogonal to each other in some way. So what that means is that when we're testing which particles are going to make, most of them, they will end up with an extremely small likelihood. So when the smoke clears, there are a few, let's say, alpha particles which are sampled over and over again. So you might end up with 1 or 2 particles, because everything else has a very small likelihood. And so what that means is that in the end, we're going to try to make inference using a sample which consists of essentially copies of very, very few particles. So there is an impoverishment of the sample there. And therefore, the density is going to be a very poor sample. We're not saying that it's, those which are there are good, but, they're too few. So I learned something new last night. So what we do here is we're going to send the grandmother on the ice to see how thin or thick the ice is, meaning that we have to cross a river and we would like to take a good path, but we don't want to fall and be eliminated. So we're going to put something which is close to expiration date, And if it survives, we're going to follow. And if it doesn't, that wasn't a good route. So we're going to go a different route. So this is the idea of this auxiliary particle. So the idea is that we're going to calculate an auxiliary predictor here. And this is this barred xj plus 1. So we're going to go ahead. And before we invest too much on this one, we are going to, so what I'm doing here is I'm essentially testing how this predictor is doing at predicting the data that we're having at this point here. I'm substituting in the formula that I had before, and I'm dividing, to keep the formula correct, and I'm reassigning this quantity here. And we think that this one is going to give us an indication, it's a score, at how well we're doing with this predictor at predicting the data. So, and I guess we're in the proper context here to talk about Darwinian sort of algorithm. So the fittest survive, not only survive, they survive and reproduced, and the weak and poor choices, they will tend to disappear here. So in this survival of the fittest algorithm, what we have is we start with an initial probability density, which may actually be rather wide if we have really no idea what's going on. And by the way, at this point, I'm not talking about the parameters. That will be another layer which comes in soon, in about 8 minutes. So we draw a particle with equal weight here from our initial distribution. And this is our initialization step. We compute our predictors here. And we compute the fitness. So we give a fitness score to all of these predictors. And so we have all these fitness scores. We need to normalize them. So here we go. We're normalizing it. So we're ranking them among the choices that we have in the predictors. And we're going to draw our indices here among these predictors with replacement using these weights here as probabilities. So those which predict well, they're going to be more likely to be chosen, and the other ones not. And then we're going to put everything in order here, and now we're innovating. So in the sense that every predictor here is going to be, well, every particle that we're really going to use, we intend to use, is going to be a little bit like the parent particle, but not exactly. There is going to be an innovation. So we are perturbing it. So it's not always the same particle. There is a term here which, let's say, which allows us actually to have more children which are not exactly carbon copies, much like phenotype and genotype here, which are similar to the parents but not equal to the parents. That allows us, if the population gets very thin, to generate more children from fit parents or fewer. So we can actually adjust here. And that's what we've done. So we have kept the particle retention to a stable level. Then what we do is, now this is a real choice. So what we are doing is we are computing, we are updating our weights. So we're checking how the daughter is doing as compared to the parent. And again, we are updating by normalizing. And if we are done, so if we are at the end of time here, we finish, and otherwise we repeat the process and we continue. Those didn't have any parameter estimation inside. So now we're going back. We have all of the same problems that we had before. So you can think of, we're doing state estimation as we move along, but with the complication that we also do not know the parameters. So, so now the propagation model depends also on the unknown theta j. So what we need to have is, what it changes here is that when we are writing now the posterior, what we have is not only xj plus 1, but we also have the theta. And the changes that it gives in the formula is that, So we're adding a theta here, and we have this additional term that we
Daniela,
need.
your microphone's come off. I can't hear you on it.
I'm speaking to, you cannot hear me?
Yeah.
Okay. I've exhausted the battery. Did I? Is it better now? Usually I'm not known for a sedated tone of voice. Okay. So, all right, so where are we? We are here, right? So what we are doing right now, we're revisiting the steps that we had before, but we're dragging along another passenger here. Before we only had the xj's and the wj's. Now we also have to keep track of the theta j's, because as we're moving along and we are doing the state estimation, we're also doing the parameter estimation. So hopefully we're gonna learn more about the parameters. And okay. Now, the way we need to come up with, let's say, a strategy for this parameter estimation. So what we're doing here is, so we have all of our particles, and let's focus for a second on the parameter component of the particle. We take all of them and we compute, if you wish, a center of mass, or theta j bar. So we're looking at, what is the mean of all of these particles, appropriately weighted. And we're also computing a sample covariance here. So then what we do is we want to approximate the marginal probability density of theta, given dj, using a Gaussian mixture model. And when we're using a Gaussian mixture model, what we use is a mixture model of this type here, where the auxiliary particle, theta, now the notation gets pretty heavy here. So theta bar j n, the n refers to the summation, the j to the time step where we are at. And this bar here resembles this one, but since right now it's customized, what's happening here is the following. If we keep doing this, and if we're sampling from a small Gaussian, think that you have a particle, and you put a Gaussian bloop on top of it, right, centered around it, and then you sample from this Gaussian. What happens is, as you move along, the Gaussian will expand. So this variance will become larger and larger. We don't want that to happen. So in order to maintain the variance, stable, what we do is we compute, and that's why we do this part here, we compute this mean, and we move the particles, which are going to be the center of the Gaussian, a little bit closer to the mean, in such a way that when we're sampling from it, and that's the meaning of this term here, when we're sampling from it, we're going to stay with the same variance overall as we would have initially. So this is, I think this is a pretty clever way of thinking. So this is a shrinkage. We do some shrinkage before we move on. So now that this gets a little bit heavy, but I'm not going to go over the details here. So we have the same formula as we had before. We had our approximation of the integral via our summation, and now what we do is we have the addition of this term here, which was not present in the previous form when we didn't have the parameter estimation. Now we're going to rewrite this, introducing, let me see, yeah, we're going to rewrite this. These are going to be our gn plus 1, and these coefficients here is the fitness, essentially, of the predictor. So now we're going to have our particle. It's going to be theta bar nj plus 1, and it's going to be x bar nj plus 1, and then we have this theta. So this is going to be the evolution of the previous one and the theta j, I think we have an index of. Anyway, so putting it all together in an algorithmic way, so we draw our sample from the initial state and from the initial distribution for the parameters. We have to do this from the beginning, so this is a new part. We compute the parameter mean and covariance, and we shrink the parameters, shrinkage around the mean, get closer to the mean, and then we compute the state predictor here. And then we compute the fitness. How fit are you? Are you going to survive it or not? Well, the more fit here, they will be chosen more. They will be reordered. And they proliferate, so they're going to have children here. And and this is how they proliferate. So this is a proliferator. So now there are two proliferators. The proliferation of the parameters and then which is going to be done with this Gaussian here. And then there is a propagation and the innovation for the particles. So updating of the weights, and we continue, and if we're not at the end of time, we recompute the mean, we recompute the sample covariance, and we repeat the process until we're done. So we continue in this fashion. Now, the problem is that we need to propagate. So it's easy to say propagate when you don't have to do it. And then when actually it comes to the propagation, we need to make some choices. And we need to innovate, innovation, of the particle as it propagates. So we said how we are going to, say, deal with the parameter part. So how are we going to do this? And I guess I haven't met yet a differential equation problem that I'm interested in, which is not from stiff to extremely stiff. So the problem that we are addressing here are typically very stiff. So the time step to stay stable, if we're using a run-of-the-mill solver, can become excruciatingly small. Also, when we put in the innovation, we need to choose it appropriately, and in this case, it will be related to the approximation error. So we stick with only the best stiff solvers here, and my favorites are the linear multi-step methods, because they give a good performance. And so we are thinking that we are propagating the particle with a good solver, and the new one is going to be the result of inexact, what would be exactly if we knew how to solve the differential equation, plus some approximation error. And right now we're not in the regime of stochastic differential equation. These are standard differential equations with unknown coefficients, so the only uncertainty which is coming is from the approximation error in the numerical integration. So now there are practical problems when one actually sits down and does this, and one is that in general, if we don't control the time step in the prescribed inaccuracy, these are a lot of particles, and especially in the beginning when we're learning about the parameters, some may require much longer integration time than others. Not all particles integrate equally. And in fact, this is like a flock of sheep, so the speed at which we're moving forward is determined by the propagation speed of the slowest particle. So we need to wait. And this is this is for some selected particles, so there was some pre-selection done, and this just shows that some of them will take much longer, may take 18, 20 times longer than others to integrate. So you're idling there. So what we did is to avoid this problem with variable propagation times, also because we had in mind parallel integration and vectorization, so we wanted to do it all at once. Instead of prescribing the accuracy in integration, we gave every particle an equal number of steps. So they're all moving, they're synchronized integration here at the same steps here. So fixed protocol, fixed propagation time, what changes is the numerical accuracy of the integrated particle. But since we can estimate that, because that's what every, let's say, decent time integrator does, we're going to resort to the tools of numerical differential equation and estimate the integration error. And what we do is we set the innovation variance proportional to the numerical accuracy. So that's customized. Each particle is going to be innovated according to how accurately it was integrated, which means that those which are unreliable, they will have a very large innovation because the actual value might be, you know, in a much bigger range, and those for which we're sure, they're going to be, let's say, not innovated a lot. And we're using linear multi-step method, and I'm not going to go over this because my time is moving along. But I mean, these are the standard formulas here. And for the stiff problem, we are sticking with the Adams-Moulton methods and the BDF, backward differentiation formula. And just to give a sense of the reason why, say why, well, just look at the stability region here. I mean, we have to take the time step so that we are inside here if we're using like a forward Euler method, while if you're using trapezoidal rule, you know, we don't have to worry, only about accuracy. And the story continues. So this is how we are doing the estimation of the integration error. What we need to do to estimate the error in the numerical integration, we need to have two methods. So we need to have either a higher order method coupled with the method with our method of choice, or we need to have a method of the same order of integration but with a different truncation constant, essentially Taylor expansion. With different, with the next term and the different numbers. That is, therefore, by subtraction, we're going to get a sense of how well we're doing. And rather than what is done in usual numerical integrators, which is like you go back and take a smaller step, here we're saying, hey, I mean, you're less reliable or you're more reliable. So we're using it as an estimator and not as a step size control. So this is how, therefore, how we set the covariance of our innovation term. So we're basing it on this error estimation in the numerical integration. And we're adding a smidget here, just in case. You know, a little bit of error is always going to be there, if nothing else, for the operations that we are doing. So importance is that here every particle is innovated according to how well it has done, let's say, in the propagation step. And now there is a little bit, a little problem here, and is that if we're using linear multi-step methods, then we're looking back, we're looking at the past. So this is an R-step method. So we would lose the Markov, one Markov property. But what we can do is, again, we restate the problem introducing a vector here. So if we're looking at it in a vectorized form, we're keeping all the states together, and therefore we're back, let's say, in the framework of these methods here. And of course, we have to put the innovation also in this vectorized form, and we're seeing that we're innovating only the new step because the other ones are simply reproduced. So for looking at the particle filter with this error control, we are continuing as we were doing before. So this is a repetition of what we were doing previously, except that now I'm declaring what I'm using for my predictor, survival of the fittest, reshuffling, and the only real change here is that now we are explaining, we're clicking on 4, and we're saying how we are assigning this innovation term. And then we do our weight updating then the question is, how well is this method working? And so we have a simple example here. This simple example has a nice property that we control everything, so we know what the solution should be, as opposed to the real example with the real data where nobody knows what the solution is. And so we are, but I mean, this is a sort of realistic-like problem. So what we have is we have 3 components to our state, x1 and x2 and x3, and x2 is blind, so we're observing x1 and x3, but we're not observing x2, and we are estimating the parameters, and what I'm showing here, I'm actually showing the progression, how the learning process for the parameters as we move along. So we're integrating over an interval which goes from 5 to 30, and we see that in the beginning we don't really know, the system doesn't know really all that much, and then what happens at 10? Well, we go back, something happens at 10. And this is reflected here, right? So all of a sudden, our confidence or sort of our support of these parameters becomes much tighter. Certainly for these two, what we see is that these two remain a little more, let's say, tentative, a little looser here. So these are the time series for the K2. This can also inform in the design of experiment where we want to measure more or where we can measure less. Now back to the PET examples. So this was our example here, and there is a V0 which is scaling the problem, which I didn't put in the model. And what we did here is we applied this particle filter sequential Monte Carlo with a linear multi-step method, and the data was given to us, and there were all sorts of uncertainties in the data. These were 3 cohorts, these 17 individuals. So HC is healthy control, CL is cirrhotic liver, HE is hepatic encephalopathy. And we estimated the parameters, and the dots, they are for LDAD. These are the LDAD red dots here. So we solved the problem using a nonlinear least square with all the whistles and bells, which did okay, but it's a dot. So what the dot here does is sometimes is inside the box. These are box and whiskers plots. And that's how we represent. So we don't have the history, but we could also have the time history here. And sometimes they are in the box, sometimes they are in the whiskers, sometimes they are at the border. So this is the estimate of one parameter, and these are the other 4 parameters that we're interested in. So what does this tell us? I guess one could say that for the most part, all happy drinkers are happy in very different ways. The 2 heavy drinkers, on the other hand, they end up in a much tighter, similar way. So it seems like some of these parameter estimations for the hepatic encephalopathy are much tighter. So there is much less of a range for this. For example, for this parameter K1 and the K5 than for those who drink normal or just a little bit too much. The rest of the interpretation of this data sort of is undergoing, and there is a lot more information that we can get here, and we have gotten, and it's like we can look at correlation, we can look at if there is correlation between parameters, or in general, if we can do scatter plots and see how related the different parameters are, and we can follow this in time or overall. So thank you.
So you have basically the whole time series from the beginning, like when you start solving it. Now let's say that there is a particle. It's actually a very nice particle. It goes to time step number 2, and the likelihood is very low. So you decide to kill him, but if you actually did go to time step number 3 and 4 and 5, you would actually do very well. Because it's just you're just fitting. Could be that the noise in time step number 2 is just a bit strange. Is that going to be a problem? That you can kill particles that because you didn't look at the whole time series for each one of them?
That's when your data comes. So, I mean, you have to have a criterion for selecting your particles. That I think is the same, in general evolution. You evolve, and then, maybe 500 years later, the person who became extinct would have done a lot better.
But that's the difference, because here you have from the beginning all the time series.
I don't have the particle. I mean, the particles that I have in the end, they are relatives of the particle that started in the beginning. You are not your great-grandfather.
Sure, but maybe killing a certain particle at step number 2 was predetermined, because if we look at step number 3, that same particle who did very poorly at step number 2 would have done great.
We don't kill, so those which have very low fitness score, we're not saying that they're going to be automatically killed. They could be statistically accepted. So there is a probability that they get chosen anyway, even if, so it's less likely that our choice will go for the particles which appear to be less fit.
So if you have enough particles, you may have one of those particles that survive, and then it proliferates later. So, but if you have a small cloud of particles, that may happen, of course.
Yeah. That's why that's why more is better in in particles. And also, when we have this type of uncertainties, we need to take a fairly wide distribution for the initial.
In this particular example, the data at the beginning is pretty harsh, because there's a huge spike. The data is really spiky at the beginning, and it's very uncertain also, because we don't really know what the input is.
It goes within like
from radial arteries, and the data come from PET scan from the brain, and so they assume that they represent the same concentration in blood, which is of course pretty.
Actually, it's injected in one. Is measured here and is controlled in the other. So we even needed to look to think about the length of the arm, and there are all sorts of uncertainties here with the data. And the data in the beginning shoots up like to, I think, 10,000, right? And then it comes down.
So obviously your Ks are treated as constant. Do they actually vary over the timescale of a PET scan? Is it reasonable to assume they're constant, or there's some variation maybe? In the model, so these are models that they feel comfortable with. This is called the K5 model. So there is a whole hierarchy of models in the PET community. Right now, they are estimated. They're thinking about the K. It's probably the K for an individual over the 50 minutes of the protocol is not going to change. It's a permeability of membrane. So it's kind of physiological parameter rather than something that would change with your metabolism or something.
I think they consider it. I think they're fairly happy to think about it as being treated as a constant.
Okay, I think we've exhausted the questions. So let's thank the speaker again. Thank you very much.